Good morning, class. Today is November the 16th, and so this is the video for November the 17th. Okay, and so first we'll go over homework 7, right? 7. And problem 1. So problem 1, you were to determine what happens to the open circuit voltage when the light drops by 1/2. And so you just use the formula VOC is equal to EB over E minus KT over E times the logarithm of A over IL, as we had previously derived. And so VOC 1 is gave you 0.6 volts, and that's equal to, and it's I told you that the oh well, you don't need this information, right? EB over E minus and I told you it was at room temperature 0.026 times the logarithm of A over IL1. And then I asked you, so the open circuit voltage is 0.6 volts for a certain light level. And then I said that the light level drops by 1/2. And so VOC2 is equal to EB over E minus 0.026 times the logarithm of A over IL1 over 2. So that's equal to EB over E minus 0.026 times the logarithm. Okay, and I'm just going to do this in a couple of steps. So basically, if you have the light level divided by 2, the 2 goes on top. And so this becomes the logarithm of A over IL1 minus 0.026 logarithm of 2. Because of the property of logarithms, that the logarithm of A times B is the logarithm of A plus the logarithm of B. But this is VOC1 is equal to 0.6 volts. And so VOC2 is equal to 0.6 minus 0.026 logarithm of 2. And the logarithm of 2 you do in the calculator, and so this works out to 0.582 volts. So you see that because, I mean, all you need to know is KT, or KT over E. And again, you know, KT over E is KT in electron volts and volts. So KT is 0.026 electron volts, so KT over E is 0.026 volts. And that's it. So, you know, part of the point of the problem was to illustrate to you that the open circuit voltage doesn't change very much with light level. And so, for example, let me see if I can do it over here on the side. So my current versus voltage relationship, okay, if this is 1, so that would be 0.6 volts. All right, what would happen when I cut the light in half, right, this is IL here. So if this is 1, 2 is half, right? So IL goes down by half, and what you see is that VOC doesn't change much at all. So, you know, as you reduce light level, the current you get goes down proportionally, but the voltage goes down basically as the logarithm, kind of. And so as you continue to go down, the curves do something like this. All right, and then problem 2, you were to do this little engine, and basically T cold is 300 Kelvin, and T hot is 450 Kelvin, and you have you know, your cylinder here, and you put air in, and that's I said you put air in at 30 centimeters. So that and A is I said 50 square centimeters. All right, and so you have the V1 is then 30 times 50, and then if you convert it, well, just leave it in centimeters, it's 1500 centimeter cubed. And I said the compression ratio is 10, so V3 over V1 is 10. So basically it goes down to 3 centimeters at the minimum piston position. And you know, a lot of people were emailing me yesterday about this N and the relationship of T hot over T cold. Okay, T hot over T cold is V3 over V2 to the N, and it's also equal to V4 over V1 to the N. So that's what you use to find V3 and V4, which you need for the answer. And you have to look up that for air, N equals 0.4. And if you know, I mean, some people wanted to have some sort of more thermodynamic explanation for 0.4, and I'm not going to provide one in this class. You know, you can look up on Wikipedia basically and see that it's related to the ratio of the heat capacities at constant volume and constant pressure, and it's actually not hard to work out. But I just don't want to add material to this course. I mean, I think it's enough to understand, you know, that T, you know, goes as 1 over V to the N, and so, I mean, I mean, I tried to hesitate, and I should have used the word adiabatic because you needed that word kind of to figure it out. But you know, spelling it out for no heat in or out, and for air, that's 0.4. And so as a gas expands, okay, in the absence of putting any heater out, just sort of letting it expand, the temperature goes down as 1 over V for air to the 0.4. All right, so getting back to the problem, then, you know, from that relationship you get that V2 is equal to, where is it, 544 inverse centimeters cubed, and V4 is equal to 413. And so you use your formula. Oh, we had to calculate beta. So beta is equal to, and you know, I guess I sort of, well, I use capital N in the formula. So N is the number of moles times the Rydberg constant, which I gave to you, and the number of moles is given by basically the density of air divided by the molecular weight. Well, first N, if N is the number of molecules, all right, we'll do N for moles in a little bit, times the weight. Okay, let me write this thing. Write it out. So the molecules per unit volume, just spell is equal to the density of air. Yeah, density of air divided by the weight of an air molecule. Okay, just think about that for a second. Okay, the density of air is like kilograms per meter squared, and so you divide that by the weight of an air molecule. That gives you the molecules per unit volume. And the weight of an air molecule, you have to use the fact that it's 80% nitrogen, and the weight of a nitrogen molecule is 28 AMU, plus it's 20% oxygen, and oxygen is 32, because this is N2, and this is O2, and you multiply that times an AMU, okay, and that's what goes there. And I don't want to get the board too cluttered now, but basically this is 1.2. Some people want to use slightly different numbers for the density of air, but using 1.2 kilogram per meter cubed, all right, you get the density of air, or the number of, and then so you get the number of molecules per meters cubed as 2.46 times 10 to the 25th per meter cubed. So then the moles per unit volume is equal to the molecules per unit volume divided by Avogadro's number, 6.022 e to the 23rd. And so it works out to basically for air that it's 40.8. All right, and so you multiply that times V1, right? Because V1 is the point at which you put in your air to get that beta is equal to 0.509 joules per Kelvin. And then plugging into our formula, W is equal to then I'll just say beta times the logarithm times 450 T hot times the logarithm of V4 over V1 minus T cold times the logarithm of V3 V3 over V2, and that works out to 98.4 joules per cycle. And then you divide that by the time of the cycle, which is, I said 1,000 RPM, so that's 60 seconds over 1,000. And then finally, the answer is 1640 watts. Which is equal to 2.2 horsepower. So, it's just working through it and plugging in the numbers. I'm sure I'm still in focus here. And it's kind of interesting, so 2.2 horsepower. 2.2 horsepower is not, a small motor engine. It's actually kind of a reasonable amount of power. 2.2 horsepower is enough to pump in some system, some coolant system or something like that. I mean, now the Carnot engine is made up because the hot water and the cold water and all that stuff. But this was to give you an idea of what's possible with these sorts of hot and cold temperature. And the point is that because the Carnot efficiency is the highest efficiency you can get, there's that. And it's telling you that if you can drive some engine, a real engine, for example, now 300 Kelvin, that's room temperature, so that's kind of fixed. But 450 Kelvin, well, that's 150 centigrade, and so you don't have to go really, really hot before you can get a fair amount of power out of an engine. Okay, so that's that. All right, onward. So okay, so electric power. And the lecture today is designed to get you at least partway to be able to do the homework. What we're going to do is we're going to do things in a little bit different order than the book. But I'll title this electric power because the objective, I forget what number, I think it was number 6 in homework 8, is to give you enough information so that you can do that last problem in the homework. And the other ones you can kind of figure out. But anyway, last time we went through that Q, actually let me, there you go. For a capacitor, Q is equal to CV. Now, that's a definition, and we went through and we figured out how to calculate using Gauss's law the capacitance of a parallel plate capacitor. Now, if you take the time derivatives of both sides of this, that means that dq dt, well, dq dt, that's I, the current, right? That's the movement of charge per unit time onto the capacitor. Now, an interesting aside here is that there are circuits where C can be a function of time. Okay, so you actually have to be a little bit careful here with the current voltage relationship for a capacitor. But assuming for the moment that C is not a function of time, you can take the C out here and it becomes C dV dt. All right. For the electrical engineers in the audience who have taken 205, where you learn RLC, and you ever forget, because the inductor and the capacitor, and one's one way and one's the other. I mean, if you remember the definition of capacitance, that capacitance is defined as charge over voltage, and you write it out and you take the time derivative. Okay, you can remember what the right formula is. Okay, so the current going into a capacitor is equal to the rate of change of the voltage on it with respect to time times the capacitance, and that follows directly from the definition of capacitance. Now let's introduce, so this is capacitors. Now let's introduce inductors. And there are various ways to do inductors. Inductors are more complicated because you kind of have to fold in Ampere's law, and it gets kind of complicated with magnetic fields and stuff like that. But the way I like to do it, okay, because an inductor is, okay, at this level you can just say it is a circuit element, right? And so I can postulate that since there's a circuit element for which the current going into it is proportional to the rate of change of voltage. By analogy, I can simply say that there should be a circuit element for whom the voltage is proportional to the rate of change of the current going into it. All right, so that's the way I'm going to lead into inductors. Inductors are interesting because, and we're not going to cover Maxwell's third equation today. We're sort of skipping over that, and then going to come back on Thursday in the interest of time. What you see about inductors is that they're related to, okay, Maxwell's third equation, and you can derive it from it, or you can derive Maxwell's third equation from this. And so there's no kind of derivation. I mean, it all just sort of fits together. And so starting with the postulate that there's some element, some circuit element that obeys this is perfectly reasonable. Now, what we know about an inductor is that it's a coil. All right. So if I have a voltage and a current, the current voltage relationship is that. And it makes perfect sense, right? Because if it is just a coil like that, if nothing is time varying, a coil is just a wire. All right. And so if there's no rate of change of current with respect to time, voltage is going to be zero because it's just a short circuit until you start time varying. And analogously to, like C is defined as Q over V, right? Charge per voltage on the capacitor. L is phi over I. Now, what is phi? Phi, okay, and you have to just follow me here. Everything fits together with inductors, and so you just have to start. It's kind of like a puzzle, right? And you could start at one end. I mean, in principle, you could start with the fact that the speed of light is a constant, and start working it through and come up with inductors. But I mean, I'm going to start at the simplest point, which is just postulating this is true. Now we know enough from Ampere's law to know, and I'll show in a bit how to calculate, that if I have current moving, I'm going to have a magnetic field. And flux, phi, this is the flux, is equal to the number of turns write it over here so that it's okay. So we have a number of turns n times b times, and I'm sorry to go back and forth between s and a for area, but it's a number of turns times the magnetic field times the area of one coil. So every time you go through a turn, you get one more magnetic flux, basically. Now, all right, and we'll just leave it at that, okay? This is I'm going to put a little wavy line under there because you have to really do an interval, okay? But I don't want to make it any more complicated for the purposes of this course than we need to be. So, and capacitors, I is proportional to dV dt. Inductors, I'm just saying, I'm going to postulate that it's a circuit element for which the voltage, you just switch I and V, is L di dt. It is a coil. It makes a magnetic field. It has n turns. Each coil has a certain area A. And so, like C is charge over voltage, L, inductance, is magnetic flux over current. And the magnetic flux is the magnetic field times the area times the number of turns. And so what we're going to do is we're going to use Ampere's law, Now what I'm going to do here, and this is in the textbook, or in the notes, I'm going to draw this coil on end. Okay, so let me draw it here. I'll draw 5 turns. I'm not sure why the wires are square, but that was the way the thing I could find. Okay, so this is I. Actually, let me draw it over here. This is I, right? And so I have a current. This thing is coming in and out of the board here, right? And so I'm drawing a cross section. I'm turning this thing on its side basically, and I'm taking a slice through it. And so this is the top of a coil, and then it comes down, and the current goes into the board there, and then it circles around and it comes out again there, you know. And so, you know, this is basically my coil with all the currents coming out of the board on the top and all the currents going into the board on the bottom. So that's I. So they're all I, okay? I mean, it's I going around like that. And as I said, this is going to make a magnetic field, B. Now, what I'm going to postulate is that if the coil is sort of long enough, that B is going to be a constant in the coil. And so now I'm going to use Ampere's law. All right, and so Ampere's law is that the integral of B dot dl is equal to mu times the enclosed current. Right, and so I'm going to write it a little bit different here, okay, by the total current enclosed. So now if I draw a magnetic or a mathematical curve here like this, and I integrate B dot dl, now let's think about it for a minute. B is going this way. So B dot dl, that's the dot product, here's dl. And so for these two parts of the curve, B dot dl is 0, because B is pointing that way. And it's an approximation because, in fact, there will be a magnetic field. We're going to approximate that outside the coil, B is 0. Now, if you think about it, it can't really be true because magnetic field lines are loops. And so what's going to happen is that B is going to go like this, okay, and the next one, you know, and it's going to form these big loops outside here. So it's an approximation that it's 0 out there. All right, so what that means is that B dot dl is approximately equal to just the part inside the coil, which we're going to say is a length Z. So let me actually do like this. So B dot dl is B, simply B times Z, where Z is the length of the coil. Easy. All right, and now, you see, Ampere told us that this integral, when you go all the way in, is equal to the amount of current that's enclosed. So if you look at it, the amount of current that's closed is actually equal to N times I, where N is the number of turns. Okay, and so now we go back over here, okay. Let's see if I can make it neat. Okay, over here, L is equal to, plugging in, N BA over I. Okay, and that's equal to NA over I times B. Now B is mu and I over Z. So of course the I's cancel because L is independent of current. So it's equal to mu A n squared over Z. So that's the inductance of a coil. So you see the methodology here, which is just like we used Gauss's law to determine the capacitance of a parallel plate capacitor. We've now used Ampere's law to determine the inductance of a coil. And sort of most importantly, is proportional to n squared, where n is the number of turns. Just as an aside, over the last, 10, 20 years, there's been tremendous efforts to integrate inductors on integrated circuit chips. And the reason why is because you want to make, like cell phones and stuff more compact. You need inductors to do things. And so there's been a great deal of effort in forming on a planar surface like spiral inductors and things like that, anything to get the number of turns up that you can do on the surface. Okay, so to reiterate, Coulomb's law to Gauss's law to the capacitor of a parallel plate capacitor. Okay, Ampere's law, sort of the first part, which is the understanding of the forces between current carrying wires, to the actual Ampere's law, okay, to the inductance of a coil. And so now we have C and L. R, we've sort of, have introduced throughout the course. I'm not going to do much more on it. R is we'll write them down. The 3 R is equal to V over I, okay, because V is equal to IR. So that's its current. Actually, let me write it out this way, so we understand RLC. Okay. That V is equal to IR. Okay. V is equal to L di dt for the inductor, and I is equal to C dV dt for the capacitor. All right, so now what we're going to do is we're going to quickly do a circuit so that you get the idea how to solve problems with circuits. And so you need to do this for the homework problem, because the homework problem is basically the same circuit, but instead you have an AC source here, which we'll get to in a second. All right, and so just as an example, if you have an LR circuit and a T equals 0, all right, the switch is closed. Okay, we know Kirchhoff's voltage law has always been, I don't know, they seem to make a big deal of it in class when you do 205, but it's just, this voltage is equal to that voltage plus that voltage. It's kind of, don't really need to think about it too much, at least I never had to. So you write down that Vs is equal to VL plus VR. And we know that because we know that VL is equal to L di dt. We know that VR is equal to IR. And so now we have an equation with only one variable, I. It's a differential equation. Ooh, that's scary. But it's not really. Now, for the more advanced electrical engineers in the audience, I know that you've learned about impedances and how to solve problems like this we're going to stick with differential equations just so that everyone's on the same level in the class. So how do we solve a differential equation? Well, we know the answer ahead of time, right? That's how you solve differential equations. And so, I mean, we're going to know that the answer ahead of time is a function like this. Okay, that's the solution to a first order differential equation like this. And so we can write out that Vs is equal to L di dt. Now what's di dt? Di dt is equal to minus b over tau e to the negative t over tau. That's the derivative of an exponential. So we can write down minus b over tau e to the negative t over tau, all right, plus r times a plus b, just plugging in, e to the minus t over tau. Okay, and now we just solve. Okay, now you solve it kind of in a series of steps because you write down that that's equal to a times r plus b times r, oops, b times e to the negative t over tau times r plus r minus, and I've lost L somewhere. That's right. There we go. R plus r minus L over tau. And and now you just sort of solve, knowing now that Vs is a constant. All right, and so we know that this has to be 0. So we know that tau is equal to L over r. And now you use your second boundary condition that I at t equals 0 is 0. Now why is that true? Well, because it was 0 before I flipped the switch, and it can't change instantaneously. Right, and so that means that if I plug in here at t equals 0 up here, I know that that's 1 and that's 1, and so then I know that's equal to RA. And so my final answer, oops, again. Actually, I'm going to use a different boundary condition. Just because it's kind of easier to see and there's less math involved. You know that at infinity, at time equals infinity, all the derivatives go away, and so VL has to go over to 0. Right, and so you know that at t equals infinity, that I has to equal to Vs over R. And what that means is that A is equal to Vs over R. And so finally you write down that I is equal to Vs over R times 1 minus e to the negative t over tau, where tau is L over R. And so if you were to plot that, it would look something like this. Okay, and again, however you want to do it in terms of the boundary condition, it's just sort of easier to recognize that at t equals infinity, the voltage across the inductor has to go to 0 because d dt goes to 0. And so it just means that I is V over R. at infinity. Okay, so I did this so that you would have an idea of how to do the homework problem, because you have to do circuit analysis. And again, if you know how to do circuit analysis with impedances and stuff like that, I would like you, it's almost necessary in fact, do the problem using the differential equation, because it will illuminate more what's going on to you. All right, now, there's some time. Okay, I have to hurry. All right, so AC power. Okay, I have to rush a little bit because I'm running out of, I don't like to make these videos too long. AC versus DC. That sounds like a band. No. So there was an issue when they started doing electrical transmission. All right. Where, okay, they had to go a long distance. And so they have some load here. RL, let's call it. Now, and this was the generator voltage. All right, and it had a big long wires going through town, connecting the generator with the end uses, and of course there's a current going through them. All right, now in order to analyze this problem, you approximate that the voltage here via the load is approximately equal to V generator, meaning the voltage drop across this wire is small. Now, if that weren't true, then you'd have a big problem because you'd be dropping all your energy across the wire. Now, if you make that that approximation, all right, you can evaluate why you want high voltages, and the reason why is because the power into the load is equal to IV at the load. And what we said that it's approximately equal to IV generator, because we postulated that the voltage drop across here is very, very small. Now, the loss in the wire, right? That's equal to I times V across the wire. Now we said V across the wire was small, so how do we calculate that? Well, that's equal to I times the resistance of the wire, right? V equals IR. And so the voltage, the loss, the power loss across the wire is I squared V wire. Okay, and I'm sorry, R squared R wire. Now, look here, okay, what this means is that the current is equal to the power delivered to the load divided by the voltage of the generator. And so this is equal to load over Vgen squared times the resistance to the wire. Now think about it. If you're an electric power company, you sell based upon the power you deliver to your customer, right? Okay, that's what you can charge for. That's the only thing you can charge for. I mean, that's that little meter outside your house turning, telling them how many kilowatt hours, you're delivering. And so that is fixed, so to speak, in this analysis. And so what this is telling you is that the loss in the wire under these constraints is proportional to 1 over Vgen squared. And so you want to make V as high as possible. Okay, and so now herein lies the problem though, because we just said that we're we're going to make the load as Vgen. Okay, so Vgen could be 600,000 volts. Now there's an outlet down here. I can't move my camera. If there were 600,000 volts coming out of outlet, I would have a big problem. I couldn't be standing next to it because it would arc at me. So this was a huge problem. Okay, what do we do? So what you do is you put on a transformer. And what that transformer does is take Vgen and Igen on this side, and it gives you I load and V load on that side, where V load is much smaller than V generator, and the point is that I load, well, I'll just say it in words, I generator, V generator is approximately equal. You lose hardly any power in the transformer. Now, okay, this is basically this thing here is that thing sitting up on the pole outside your house. It's taking the high voltage in those wires, which by that point, there's been a number of these things that have stepped down the voltage. But outside your house, that could be, say, I don't know, 1,500 volts or something like that, which is still quite high. And that cylindrical shaped object there takes that and converts it down to, well, it's a little bit more complicated, essentially 120 volts coming out of that outlet. Now, what is this thing? That is a coil. All right. All right. And furthermore, you draw it well enough. It's two coils like this where I have a piece of iron or some other ferrite material that goes through both coils. And now if you look at this, okay, this is a coil, so I know that V is equal to L di dt. Okay, let's walk through it here. I'm going to erase this. Okay, this is a transformer. All right, and we have then that V generator is equal to L1, if this is side 1 and this is side 2, L1 di, I'll just put 1 dt, all right, and V load, well, I'll write up Jim, and V load is equal to L2 di load dt, right, and we know how to evaluate inductance now. Okay, I1 is equal to V 1 over L1, right? That's our definition of inductance. I2 is equal to V2 over L2, all right? And what this means, because I1 is proportional to N1, this is proportional to N1 squared, right? We found that. Same thing here. This is proportional to N2, and this is proportional to N2 squared. And it's because the magnetic field is conveyed through the iron that we have that I load over V over I generator is equal to N1 over N2. And then from these relationships, because of the voltages being proportional to I and G, we'd have that V load over V generator is reversed, N2 over N1. So you step down, because N1 is smaller than N2, you step down the voltage while you're stepping up the current by the same ratio. And so this was Tesla's contribution to mankind. I mean, he basically determined how to make this thing. And the only thing is, right, you won't get any voltage on the other side unless you have a changing current. And so it had to be AC. So AC won because you could make transformers. All right, now we're bumping up against my artificial time constraints. But basically, let me rewrite this over here. Well, I mean, you can remember it. I mean, step up, step down. So now, what we know is AC1. So let's do AC power. All right. So I'm going to say my voltage is V peak sine omega t. My current is I peak. Now I'm going to say for the moment it's sine omega t. We're going to go through that in a second. All right. So IV, that's my power, AC, is IP, VP sine squared omega t. Now, sine squared omega t, right, looks like this. All right, it has an average value of I peak V peak over 2. So WAC average is equal to IP VP over 2. Now, we're going to define, I've already out. We're going to define something called IRMS. That's going to be defined as IP over root 2. And we're going to define VRMS as VP over root 2. So that means that W average is equal to IRMS VRMS. Because I mean, you multiply, you get to 2. All right, and in fact, if you use an AC voltmeter or an AC current meter, it will give you the RMS values, which are basically the peak values divided by root 2. Okay, now that is if I and V are in phase. All right, if instead I is equal to I peak sine omega t plus V. Now, why would that be true? Well, that's the point of your homework problem, the last one. That'll be true if there's inductance in the load. See, if it's purely resistive, then I and V are in phase. But if there's inductance or or capacitance, I mean, you would get some phase variation. All right, so then, okay, what is WAC? WAC is equal to then IP VP sine omega t sine omega t plus phi. And this, you expand, right? And, you know, you use your trig rules. And that expands to cosine phi sine squared omega t plus sine phi cosine squared, or I'm sorry, sine omega t cosine omega t. Right? You just, if you expand this, you know, this you basically use your, you know, sine of a plus b is equal to, you know, sine a, sine b, you know, that thing. So if you expand this, it is that. Now this is sines and cosines, so this averages to 0. This, we already know the answer. This averages to 1/2. So that means the WAC average is equal to cosine phi times IRMS, times IRMS VRMS. The point being that all you do when you put it out of phase is you add this term. And this is called the power factor. TF. That is, cosine phi is the power factor. Not phi, okay, cosine phi. And so when you calculate, well, we'll go through it more, but basically, like your little kilowatt hour meter, if you play with it, you'll see that it calculates power factor. And so if you have an out of phase circuit, like in your homework problem, all right, the power then is still IRMS, VRMS, but then you have to multiply times the power factor. And you see that if phi equals 0, the power factor is 1. So you revert back to your original formula. All right, that's it. And we're at 58 minutes. Perfect. My goal in these videos is not to exceed 60 minutes these days, because, you know, that's, you know, an hour seems like just about as long as, you know, anyone wants to watch me do anything. So that's it for today, and we'll discuss this in the chat session tomorrow.